Electron energy. So the energy of an electron and its position are complementary. They're related. Kinetic energy, we keep seeing this equation over and over again. 1/2 the mass times the velocity squared. So the velocity of an electron is going to affect its energy. For an electron with a particular energy, the best we can do is describe its position in terms of an orbital, which is a probability distribution map showing where the electron is likely to be found. I'll give you an analogy for this. So let's say this is my house, which is not quite the right shape, but that's okay. So I have a 7-year-old, and he's a little bit like an electron. He's kind of unpredictable. And so if you were to just, like use one of these Find My Friends apps, I actually thought about getting a GPS for him to wear around his neck or something, but it was going to be too expensive. But if you had GPS tracking on Andrew and you were to, check on him every 5 minutes and see where he is, and it's like, okay, he's over there, and now he's here, because he wiggles around when he watches television. And then he went and got a snack, and then he went and used my bathroom. Now it's nighttime, he's sleeping in my bed, and now he's on the floor next to my bed. And he actually went into his room and in the hallway, and there he is back, doing stuff in the living room. You'd get a kind of a picture of where you're more likely to find Andrew. Okay? You're probably not going to find Andrew in Tommy's room because he knows that he shouldn't go in there because Big Brother will get mad at him. But so you get this distribution, a probability distribution map. So can I say, well, Andrew is here? No, I can't, just from this map. But I can say, well, Andrew is probably over here. It's less likely that he's over there. And that's the best we can do with electrons. And so these regions in which the electron is likely to be found are called orbitals. So that word is very similar to the word orbit that's used in the Bohr model. An orbit is like a planetary orbit going around in a basically circular path, very predictable. Electrons don't do that. The reason we need to look at the energy of electrons is that the properties of atoms, many of them, are directly related to the energies of the electrons within them. So Schrodinger of Schrodinger's cat came up with an equation. Here it is, as much as that means to any of us. This allows us to calculate the probability of finding an electron with a particular amount of energy at a particular location in the atom. And when we solve Schrodinger's equation, the solutions are wave functions, and that's this, I can't remember the name of that Greek letter. But they're wave functions. And if we plot that wave function squared, we can get kind of a representation of the shape of an orbital. The calculations are going to show that the size, the shape, the orientation in space of the orbital are determined by 3 integers, 3 whole numbers that are in that wave function. And those numbers were put into the wave function to quantize the energy of the electron. Because we know from the emission spectra of different atoms that the electrons can only have particular energies within the atom. And so the wave function, in order to describe the atom, must also have particular levels of energy. So those integers are called quantum numbers. There's the principal quantum number. This is n, the angular momentum quantum number, L, and the magnetic quantum number, m sub L. There's a 4th quantum number that's not an integer, and that's the spin quantum number, m sub S. So let's look at each of these individually. The principal quantum number, n, is, it corresponds to Bohr's energy levels. So in Bohr's energy, Bohr's model of the atom, remember we had a nucleus, and then we had n equals 1 and n equals 2. So we had a second energy level and a first energy level, a lower energy orbit and a higher energy orbit, and as the orbits got farther from the nucleus, n increases and the amount of energy that that electron has increases. And so this principal quantum number corresponds to that, and so it's convenient. I prefer to think of the Bohr model because it's easier to think about, it's easier to visualize. I can picture the solar system, but I have to remind myself that's not really what the electrons are doing. So n can be any integer greater than or equal to 1. You can't have n equals 0. So it starts with 1 and goes up from there. The larger that n is, the higher the energy of the electron and the larger the orbital size. The area, the volume in which that electron is likely to be found gets larger and larger. Just like when we go to higher n in the Bohr model, the orbits get larger. So there's some correlation here. For the hydrogen atom only, we can calculate the energy in any given level using this equation. Minus 2.18 times 10 to the minus 18th joules times 1 over n squared, where n is that principal quantum number. This energy is negative because the electron's energy gets lowered by its interaction with the nucleus. Lower energy is better. Think about, I've always seemed to have a teenage boy or two in my house. And teenage boys prefer to be horizontal. Sleeping is awesome in their book. Texting, watching TV, listening to music, but they like to be horizontal, low energy. They'll get up and do things. They go to school, they go to football practice, they play basketball, whatever, but they always return to this lower energy state. Just like a boulder rolling down the hill. Why does the boulder roll down the hill and not back up the hill? Its potential energy is lower at the bottom of the hill. So it's going to move in a way to lower its energy. So electrons do that as well. By interacting with the nucleus, the energy of the electron is lowered. There's a force of attraction between the positive nucleus and the negative electrons. So as n gets larger, the energy of the electron gets larger. And we also see that the difference in energy between the orbitals gets smaller. And that has to do with this math function. So if we look at this, so the difference in energy between n equals 1 and n equals 2 is represented by this distance. That's large. The distance between n equals 2 and n equals 3 is smaller. And between n equals 3 and n equals 4, it's smaller. So as n increases, the difference between that and the previous level gets smaller and smaller and smaller. And these are the values for hydrogen for these different principal energy levels. Any questions? So that's the principal quantum number. The angular momentum number determines the shape of the orbital. And we'll look at what the shapes are later. We said that n can be any whole number starting with 1. L is restricted based on what the n is. And so L can be an integer from 0 up to n minus 1. Each value of L is given a letter designation. And you might think it would be nicer if they made these A, B, C, D instead of S, P, D, F. There is historical background for that. I always forget what S stands for. I looked it up once. P is for principal, D is for diffuse, F is for fine, and they came about from descriptions of the lines in the emission spectra. So there's a reason that it's not A, B, C, D. If L equals 0, that's called an S orbital. L equals 1, a P orbital, etc. The magnetic quantum number is the number that specifies the orientation. It's how it's aligned in space relative to the other orbitals. And the values here are from minus L to plus L, including 0. So if L equals 2, then you can have 5 different values of M sub L. You can have minus 2, minus 1, 0, plus 1, and plus 2. If L equals 0, you only have one value, just 0. So I'm going to tell you all of this, and then we're going to keep working with it, and hopefully it'll kind of come together before the end of this lecture. The spin quantum number specifies the orientation of the spin of the electron. This is a fundamental property of electrons, and all electrons have the same amount of spin. You can think of this like a top spinning. My son plays with Beyblades, fancy little tops, and some of them spin clockwise and some spin counterclockwise. That's the easiest way to think about it. But the electrons are not spinning like tops. But an electron can have positive spin or negative spin. And so M sub s is either plus 1/2 or minus 1/2. So each combination of N, L, and M sub L, the first 3 quantum numbers, describes a particular orbital, one orbital. And each orbital can hold 2 electrons. Orbitals with the same value of N are said to be in the same principal level or principal shell. And orbitals with the same values of N and L are in the same sublevel or subshell. Okay, so here's the picture, and then I'm going to give you a stupid analogy. So if N equals 1, then L can only be 0. L can be 0 up to 1 less than whatever N is, right? So if N is 1, L can only be 0. If N is 2, we could have 0 or 1. So these are 2 sublevels of this principal level. When N equals 3, we have 3 different values possible for L. If we look at, let's just stay up here. If L is 0, M sub L ranges from negative L to positive L. So if L is 0, M sub L can only be 0. And so that's one orbital. If L is 1, we can go from negative 1 up to positive 1, and 0 is included. So there's 3 different orbitals here. For L equals 2, we have 5 orbitals. Okay. Now, all of this is really, really hard to visualize because, we can't even draw really great pictures of it. So I was trying to come up with an analogy to help students understand these levels and divisions. And the best thing I could come up with is a hotel. So I call this the Electron Hotel. And this is in Mrs. K's chemistry land. So this is the first floor of the hotel, and this is the second floor and the third floor. It's kind of a weird hotel because as you go up, there's more and more rooms. It gets wider. It's like an upside-down pyramid. Each of these sublevels is a room. So on the first floor, there's 1 room. On the second floor, there's 2 rooms. On the third floor, there's 3 rooms. Guess how many rooms on the 4th floor? 4. 4 rooms, okay? So the number of sublevels equals the principal energy level. The number of floors in the number of rooms on a floor in the hotel is equal to the number of that floor. And then these individual orbitals are the beds. So there's different kinds of rooms in this hotel. You can get like the queen room and the king room, right? It's got 1 king bed or 2 king beds. Hotels come like that, right? So this is the S room. S rooms all have 1 bed. P rooms have 3 beds. D rooms have 5 beds. Look at this pattern, 1, 3, 5. On the 4th floor, there's a 4th room. It's the F room. Guess how many beds it has? 7. Okay. just like in a hotel, we allow 2 people in a bed in a hotel, right? 2 electrons in an orbital, okay? The spin, okay, so this is some like all-male convention, okay? And do guys who are like just acquaintances, are they going to be happy about sleeping together in a double bed? No. Would one of you guys at this bench be willing to share a bed for a night with one of the guys from that bench?
Absolutely not.
Absolutely not, right? So one of you you'd probably flip for it or fight for it, and one of you would sleep on the floor instead, even though the floor is filthy, right? I know this.
There's no couch?
There's no couch. No couch, no bathtub either, just a shower. Anyway, so this hotel, it's kind of a weird hotel because it's in my chemistry land, right? They don't allow people to sleep on the floor. So what are you going to do?
I'll get another room.
Get another room. But you're cheap. So there's money involved here. And the money corresponds to energy. So the room on the first floor is the cheapest. The rooms on the second floor are more expensive. The room on the third, as you go up, things get more expensive. Also, as you go away from the elevator's here and the ice machines and stuff, and so you really would rather not be in the 3S room, but you'll have to pay more to get over here because it's quieter. Okay, so what would 2 guys do if they have to sleep in the same bed? I didn't mean to do that. Well, I visited Fort Snelling once on vacation, and we went into the barracks, and they've got these bunk beds, and they're like, I think even narrower than twin beds. And 4 soldiers slept on one bunk bed. They slept head to toe. And so one would sleep with his head on one end of the bed, and the other would sleep with his head at the other end of the bed. Because your bodies fit together better that way, because your body is bulkier than your legs, right? I'm sure they kicked each other in the face all the time. It was really cold in Minnesota in the winter, right? And they didn't have central heating in the 1800s. And so they kind of needed to sleep together to stay warm. So this is what the electrons do. They're essentially forced to share beds, and so they go head to toe. So there's no, we're not sleeping together, right? We're just in the same bed because we have to be, right? So head to toe. This corresponds to the spin of the electron. So this is spin up and that's spin down. This guy has his head at the headboard and this guy has his foot at the bottom of the bed, okay? So as electrons come into this convention and they're coming into the hotel, they're going to take the cheapest rooms first. These are not luxury accommodations. You don't want to pay more than you have to. So the first electron is going to come in and he's going to sleep in that bed. The next electron is going to come in. Yeah, this level is available, but funds are tight. And so he's going to suck it up and share a bed with that guy. Then the next ones come in. Well, the 2S room is the next cheapest. So he's going to go in there. The next one comes along. He's going to go in there, sleep head to toe with that guy. The next cheapest room is the 2P room. So the next electron goes in there. This P room has 3 beds in it. So the next electron coming in, is he going to share a bed with the first guy or take one of those empty beds?
No, I'll take the empty bed.
He's going to take the empty bed. There's no question. So he's going to take his own bed and hope nobody else comes, right? And then the next electron is going to take his own bed. The next one that comes in is going to have to share. They're not willing to pay more to go up to the next most expensive room. And so they're going to fill in like this. And then they'll go up to the next floor. And you'll get 2 in here. When you get over here, again, they're going to take their own beds. If they can, they're not going to share unless they have to. Okay, so energy corresponds to money in the hotel. Electrons correspond to people. Floors correspond to principal energy levels. Rooms correspond to sublevels, and the individual orbitals correspond to beds. Okay? Any questions? So these are some general observations. The first one I think is the most important. The number of sublevels within a level is equal to n. So the number of rooms on a floor is equal to the floor number. These may or may not be useful. I'm not even going to talk about them. Oh, I want to go back to this just for a minute. These quantum numbers allow us to describe each electron. Each electron is going to have a unique set of quantum numbers. And in this hotel, we can use the floor number and the room type and the bed number and whether they're sleeping right side up or upside down to indicate which electron we're talking about. So let's pick one of these guys. Let's pick this guy right there. What are the quantum numbers that describe him? Well, n equals what? N equals 2. And L is 1. Okay? 1 and P, L equals 1 and P go together. And then his M sub L is in plus 1. So there's 3 beds in there. There's a -1 bed, a 0 bed, and a +1 bed. And so M sub L equals +1. And then his spin, he's sleeping upside down. That's negative. So his M sub S is -1/2. Every electron in that hotel is going to have a unique set of those 4 numbers. Now, this electron has 3 numbers in common with the other guy in the bed. He has 2 numbers with the other guys in this room. He has 1 number in common with the other guys on the floor. Okay? So then let's do an example like this. List the quantum numbers associated with all of the 5D orbitals. Well, we've got quantum number, not M, N, L, M sub L, and that spin quantum number refers to individual electrons. It doesn't describe orbitals. So for 5D orbitals, what does N equal? 5. And the D would correspond to what? 2. 0 is S, 1 is P, 2 is D. So this is L equals 2. And then what are the possible values of M sub L? -2 up to +2. So -2, -1, 0, +1, +2. So if we made a table, N and L and M sub L, we could have 5, 2, and -2, 5, 2, and -1, 5, 2, and 0, 5, 2, and +1, 5, 2, and +2. How many different orbitals are there? 5. 1, 2, 3, 4, 5. Any question?
Why is L 2?
L is 2 because that's what D means.
That's even 3.
It's a little confusing because it starts with 0. So if you went 1, 2, 3, we'd expect D to be 3, but it starts with 0. Any other questions?
So D would be in -1?
Pardon me? D can't be -1. The 5D,
Yeah, D would be N -1.
Well, L can go up to n minus 1. And so for level 5, principal quantum number 5, you could have an L as high as 4. But we're told it's a 5d orbital, and d corresponds to L being equal to 2. Any other questions?
You don't have to list out the spin.
I don't need to list the spin here because it's talking about the orbitals and not the electrons. So each of these is an orbital, and we could have an electron with a positive spin and an electron with a negative spin. So how many electrons could we hold in this group of orbitals? 10. 2 in each orbital. Okay, here, each set of quantum numbers is supposed to specify an orbital. But each of these sets of numbers has one quantum number that's not allowed. Replace that with one that is allowed. So here we've got n equals 3. Is that an okay value for n? Yeah, it is. L equals 3. If n equals 3, can L be 3? No, it can't. It can be 0, it can be 1, or it can be 2. Okay, so that one is the wrong one. It could be 0, 1, or 2, but then we have to make sure that the one we pick here is going to work with m sub L. M sub L can go from minus L to plus L, right? So this m sub L being 2 tells me that L must be at least 2, right, for m sub L to be 2. So we're going to choose this one. Let's look at the next one. N can be 2, that's fine. If n is 2, can L be 1? Sure. Can m sub L be negative 2? Nope. It could be negative 1, or it could be 0, or it could be 1. 0, negative 1, or plus 1. And here, any of those is okay with the first two. Let's look at this last one. So n is 1. Can L be 1? Nope. What does L have to be? 0. Okay? Any questions? Okay, so let's think back to those emission spectra, and we can explain what's going on there. So in the emission spectra, we saw discrete bands of light with specific wavelengths. Each of those wavelengths correspond to an electron transition between orbitals. The orbitals have different energies. When an electron moves from a low energy orbital to a higher energy orbital, it has to absorb energy. So in the hotel, the way this works, this hotel is in Las Vegas, and so what happened is one of those electrons went to the casinos and he won some money. He absorbed energy. And he's like, I don't enjoy sharing a bed with this guy. I've got some energy. I'm going to buy a better room for tonight so I can sleep in my own bed. So the electron absorbs energy, and if it gets the right amount, it can jump up to a higher energy level. Well, it can't stay up there. The guy won some money, but it's not an endless source of money, and so eventually he's going to have to come back down. When the electron comes back down to a lower energy orbital, it emits the same amount of energy that it absorbed to go up there. The guy has spent that amount of money, right? And now he has to come back down. Well, that energy being released comes out as a photon of light. And the energy of that photon corresponds to the energy difference between the orbitals. So if the electron absorbs energy and goes from n equals 1 up to n equals 3, It can't stay up there. Let's say it falls back to n equals 2. It's going to emit a photon of light, and the energy of that photon is going to equal the difference in energy between these two levels. That's why we see only particular wavelengths of light being emitted, because there are only particular transitions that are allowed. So to go to the higher energy state, the electron has to gain the correct amount of energy. It has to be just the right. It's like the bus driver who doesn't make change. You have to have the exact fare. It goes up there, it's unstable, it's going to come back down. I think I kind of said all of this already. We can predict the wavelengths for hydrogen. Hydrogen is simple, and we can actually calculate the energy differences, and we can figure out what principal quantum numbers are changing when the electron relaxes to a lower energy state. So for an electron in some energy state n, there are n minus 1 energy states it can transition to. Therefore, it can make n minus 1 lines. So if it's in, if it has n equals 3, right, it could go from 3 to 2, that's one transition. It could go from 3 to 1, that's a second transition. There's two possible transitions. The Bohr model predicts all of this very well for hydrogen. The quantum mechanical model also predicts it very well for hydrogen. The problem with the Bohr model is it only works for this one electron system. So now we're getting into some of the calculations we're going to be doing in lab today. So we can say that the change in energy is the final energy minus the initial energy. Delta is always final minus initial. So the energy of that photon equals the difference in energy between the levels. And so it's the final level minus the initial level. Well, we said earlier, let me write this in here. We said earlier that for hydrogen, the energy of an electron in some level is 2.18 times 10 to the minus 18 joules times 1 over n squared. Bless you. So this is the energy of the final state of the electron, and then we're subtracting the energy of the initial state of the electron. So this is a big old mess, but we can factor out this negative 2.18 times 10 to the minus 18. So it's that number times 1 over f squared minus 1 over ni squared. And that is the change in energy experienced by the electron. Well, the change in energy of that electron within the atom, it's going down in energy, it's releasing energy out. And so the photon is going to have that same amount of energy, but the sign is going to be opposite. This equation here is a rearrangement of the one we saw earlier, where the energy of a photon of light is hc over lambda. So knowing the energy transitions, say it's going from 5 down to 2, we can calculate delta E. You change the sign, now you know what E for the photon is. You can plug that into here, and you can calculate the wavelength of the light. It's pretty cool. So in the hydrogen atom, here we have n equals 1, 2, 3, 4, 5. If n were infinity, that means that that electron has been ejected from the atom. It's become a hydrogen ion. So it's just left the atom entirely. We see transitions all the way down to the ground state, n equals 1. Because hydrogen only has one electron. That electron is going to hang out in that lowest cost room at the hotel. So it's going to hang out in the n=1 room whenever it can. But if it gets bumped up to 5, it can jump all the way back down to 1, or it can jump down to 2, or it can jump down to 3. It could also go down to 4, but that's not shown in the picture. And so we have these different possible transitions. These 3 transitions give off photons of light that are within the visible range. We can see them, and the colors are indicated here. These transitions are lower in energy, the difference is smaller, and these give off infrared wavelengths. We can't see that with our eyes. These transitions are larger in energy and are in the ultraviolet region. So those are the 3 transitions that we can actually see. And we're going to set up hydrogen lamps today and get out spectrometers, and we're actually going to see the lines. It's really neat. Any questions? So determine the wavelength of the light absorbed when an electron in a hydrogen atom makes a transition from an orbital in which n=2 to an orbital in which n=7. Really important to identify which is initial and which is final. So it's going from 2 to 7. So this is the initial, n=2 is the initial, and n=final is, n=7 is the final. This is the light that's being absorbed. The number is going to be the same for light that's emitted, but the sign is different in terms of energy. So here we have energy being absorbed. Well, we need that equation. The change in energy is equal to minus 2.18 times 10 to the minus 18th joules times 1 over its final minus initial again. And F squared is 7, and N initial is 2. And you do have to be careful on your calculator. So negative 2.18 times 10 to the minus 18th times the quantity 1 divided by 7 squared minus 1 divided by 2 squared so the amount of energy that the atom has to absorb is 5.01 times 10 to the minus 19th joules. It's positive because it's going from the lower to the higher. The atom is absorbing energy. How can we find the wavelength of the light? That other equation. Lambda equals hc over E. So 6.626 times 10 to the minus 34 joule seconds. Speed of light, 3.00 times 10 to the 8th meters per second. And the energy is 5.01 times 10 to the minus 19 joules. And let's check our units. Joules cancel, seconds cancel. So we're going to end up with a unit of meters, which is a length, and we can measure wavelength in meters. 6.626 times 10 to the minus 34 times 3 times 10 to the 8th divided by 5.01 times 10 to the minus 19. So I get 3.97 times 10 to the minus 7th meters. Any questions?
How are you getting this, the H and C number, what are those representing?
H is Planck's constant. It's 6.626 times 10 to the minus 34 joule seconds. And C is the speed of light, 3 times 10 to the 8th meters per second. Any other questions? Yes?
So those sort of questions on the exam, do you have to memorize the type thing?
On the hour exams that I give you, I'm not talking about the final, I will give you a bunch of equations.
Okay.
They're not going to be labeled or anything. But this with the N's and the F's, if you need it, would be in there somewhere. Yep.
Okay.
Any other questions?